All right. This is the lecture for the last lab of the semester. Okay, so um, in the prior lab, you designed the forwarding unit and pipeline control unit, and most of you have submitted that lab already. And I went through and just briefly looked at um, what some of you have done, and so far it looks pretty good. I need to obviously officially grade all of these labs. I've got a lot of grading to do. I'm a little behind on that. But anyway, so what we do this lab is we actually put all of our components together. This is sort of the culmination of everything you've done this semester. You know, we started with the single cycle processor. Well, actually, I mean, really, we started with designing the individual components within the single cycle processor, which would be your register file, your ALU, and your ALU decode unit, your instruction decode unit. And then we were able to put all those together in our single cycle processor. And the single cycle processor allowed us to actually test all of those individual components. And so now what we're going to do is we're going to take those individual components and we're going to put them in another top level file that implements the pipeline data path. And part of that data path, of course, is the forwarding and pipeline control units that you built last time. So didn't really have a chance to test those last time. So then the whole idea is at this point, all your individual components from the single cycle design should be working. You use the single cycle data path to test those, and then now we'll combine that with the pipeline control unit, the forwarding unit, and describe a pipeline data path. So we're not going to use the single cycle data path. That was prior labs work, and really the whole point of that was to help you understand how data should flow through a data path. Okay, and so this pipelined data path that you're going to describe in lab this week will take place of that single cycle data path. The only modification we have to make to the components we've built this far is the register file. We need to change it so that writes happen on the falling edge of the clock. Okay, if you recall, in some of the pipeline diagrams that we talked about in lecture, we have this concept of register writes happening at the beginning of the clock cycle, so the first half of the clock cycle, and then reads happening at the end of the clock cycle. If you remember, based on the latencies that I gave you for some of your homework problems where you were trying to figure out the critical path through the single cycle and pipeline data paths, the register write and register read operations did not take nearly anywhere close to a full cycle to complete. So what we're doing is not completely out of the ordinary. Okay. Now, depending on your target technology, it may not necessarily like having you mix positive and negative edge triggered flip-flops, which is what you're doing when you make the register file sensitive to the falling edge of the clock. That's a negative edged triggered flip-flop is what's going to actually be used for that. But it turns out FPGA logic is quite forgiving and doesn't mind us doing this at all. Okay. Oh, just real quick, the lab, I set the lab date for the 16th of May, which is officially the end of the semester. Okay. Usually after that, I start getting nasty grams about turning in grades. Now, that being said, with the pandemic that we're in the midst of, I'm not sure that that's going to be the case. Okay. Now, I know they wanted to ensure that professors did all that we can do to ensure that graduating seniors are able to graduate this semester. So with no hiccups to that. So if you're a graduating senior, it definitely makes this deadline more important. Um, Anyway, so yeah, the 16th of May, and that'll give me some time to to grade it and submit grades and whatnot. Just to recap, these are the instructions that we are supporting. This list should be identical to the single cycle. If for whatever reason it's not, let me know. That means I made a mistake. Okay. Um, so we're not asking you to support any additional instructions. Now, had we had a full semester, where we could actually meet in lab and whatnot, I've actually got 2 or 3 labs that that follow this one. The lab that would immediately follow this one, had we had a full semester and were able to meet in person, would be adding support for jump and link and jump register, which would allow our processor to support procedural calls. Okay. Right now, we actually don't have the ability of handling procedure calls with the small subset of instructions that we're supporting here. And then continuing on, if we really had a successful full semester, the next lab would have been to include support for exceptions in our processor. And that's actually the kind of the bare minimum instruction set that I started with before I actually started designing what I've later named Pete, the microprocessor, which is a real processor that's in use at Sandia. And so what I did is I had started with, because I was designing these labs for the graduate computer architecture class at Texas A&M, and they the students, I had them um, do all of that and implement exceptions, and in addition to that, an instruction cache as well. And so obviously, when I converted this lab to an undergrad lab, I had to chop off a number of labs. But anyway, when I took that core that I had developed as the solutions for that class, and the following semester, I actually iteratively got the design to run C code. So I did that with the aid of the reserved instruction uh, exception. So the reserved instruction exception, also known as an undefined instruction, is basically an exception that's thrown when the decoder can't decode the instruction. So what I would do is I had some crypto code that was compiled in C, and I took that assembly and I ran it on the processor, and then I encountered a reserved instruction when I reached an instruction that I hadn't implemented. So I went and I read the manual and I went and implemented that instruction, and then I would run it again, and then I would hit another instruction that I hadn't implemented. Now, of course, I would get a little bit further in the code, and I just kept doing that iteratively until I had basically um, designed in all the instructions where I could then successfully run that C code. It was a very proud day when I was actually able to run that entire public key encryption algorithm in C on my own processor. So it was very rewarding. And then the following summer, that summer, because I started the course material in the fall of, I think it was 2011, and then the spring of 2012 was when I got it to run C code, and then my colleague Don and I worked that summer then to get it to actually run C++ code. So that was the humble beginnings of the Pete microprocessor. And so, so I'm really going out on a tangent here, but if you're not that far off from being able to develop a real product. Okay. Anyway, so okay, but this small subset, like I say, we're stopping here. But you can imagine there could be at least 3 additional labs after this. Okay, so the background information just kind of recaps some things that we had already talked about. We're we're not implementing a branch predictor. That was actually an additional lab because I think I had my graduate class had I think like 4 or 5 more labs after this one, and so they actually implemented a branch predictor. And so but we're not. So we're using the assume not taken. Okay. Um, and and of course we have to have the flushing uh, refetch mechanism. We went through this diagram in quite a bit of detail last lab lecture, so I'm not going to go through it again, just in the interest of time. Uh, but you know, you can go back and listen to that portion of the video if you want a recap. Um, but anyway, so um, the main part that we're going to be implementing in this lab, well, we're basically going to be implementing all of what we see in Figure 1. But we're going to be adding in these pipeline control registers right here. Okay, and I've got um, a, a notation that I recommend. Okay, a convention that I recommend you use for naming your signals. And the reason is because, the single cycle design, we didn't have duplicate signal names, but in the pipeline design, we do. Okay, so um, for example, we have signals that are generated in the decode unit, and then they flow down to the various pipeline stages. Okay, so the same signal that starts at the decode, okay, makes its way all the way from, could make its way through the execute, through the memory, and through the write back. And so we want to have a way of differentiating between the various signals. And then if you follow the convention that I provide for naming your signals, you'll also be able to tell based on the prefix and postfix. You'll be able to tell where the signal is headed and where it was originated. Okay, so that's mostly what I'm going to spend time talking about now is the actual naming convention, because it's very important that you follow a very consistent naming convention. I always say that one of the hardest things you do when you're describing code in an HDL is coming up with good signal names. Okay, I spent a lot of time thinking about what the signal name should be, and then a lot of times I come up with a signal name, and then later I end up having to change it just because it doesn't make any sense. And so it took me a little while to come up with this convention. In fact, I don't even think the first versions of our processor used this convention. I think Don and I ended up coming up with this convention to clarify all the different signal names. I had a somewhat of a pseudo convention when I first started the project, but we eventually settled on this convention. Now, I think I mentioned this in the single cycle design, but I'm going to mention it again for the pipeline design. Um, you, there's nothing about the language that enforces you to describe logic in a certain order. Okay, but it makes your life a lot easier if you do so. Now, of course, there the syntax of the language requires that you declare signals in one location. You declare components in in a particular location. But then within the architecture part of the file, you can instantiate components and have assigned statements to signals and have process blocks in whatever order you choose. It's not like a C program, where a C program, kind of starts at the top and goes down, right? If you have your main and then you know that the code is going to execute sequentially. Now, of course, you'll have you might have for loops, and hopefully you don't have any go-to statements or anything like that. There are some languages that are just littered with go-to statements, and they're almost impossible to read. Fortran is one of them. Um, but um, but with the so again with C, it kind of follows from top to bottom with some looping in between, but that's not the case with an HDL, and that's one of the things students really struggle with um, when they're using an HDL, a hardware description language, is that you could describe things in any order really, because everything's sort of happening in parallel. Everything's happening concurrently. Concurrently is the better word for that, and so you might have a process block that describes a register, okay, and how it works, and then you'll have an assign statement that assigns, takes that value from the register and does some arithmetic computation to it and assigns it to those signal. Well, all of those operations are happening concurrently, okay? Just like in our pipeline, okay, the fetch is happening concurrently with the decode, which is happening concurrently with the execute, happening concurrently with the memory, which is happening concurrently with write back. Okay, all of those things happen concurrently. So you could describe your fetch stage, at the bottom of the HDL file, the architectural section. Okay, um, or um, you could describe it in the middle somewhere. It's really up to you. Or you don't even have to divide up a particular section of your HDL to describe the fetch stage. It could be intermingled, but you would basically create unreadable, unmaintainable code. Okay, so what I recommend is that you kind of you lay things out in your HDL in the order that they would appear, where top to bottom is left to right, where we've drawn these diagrams countless times on the board or the virtual whiteboard, where we see data flowing from left to right, starting in the fetch stage and ending in the write back stage. And so that's the way I recommend you lay out your HDL file. Okay. So I started out with comments, and one of the things is when I develop code, I actually have as much, if not more, comments than I do actual HDL. Um, or synthesizable code, right? And that's that's sort of my style, but before I even write code, I've already thought about how data should flow through a given architecture. And then I start by describing it in comments, and then I basically um, flesh out the file by adding functionality that does what the comments describe. Okay. So here we see, I say, this HDL source file describes the basic 5-stage pipeline. I'd like you to read these comments. I want you to read them. Okay. And I lay out, what happens in each of the different stages. Okay. And then, and this is from a high level, right? Of course. Um, and then what I do is I actually explain my signal naming convention. Okay. So the naming convention has a prefix followed by the signal name, or an underscore followed by the signal name, followed by an underscore and a suffix. Okay. Um, so the prefix identifies the location within the pipeline where a given signal comes from. Okay. So and if two stages are specified for the prefix, then the signal comes from the pipeline register between those two stages. Okay. So for example, we'll have a signal called load. Okay. And if and that comes from your decoder, of course. Actually, did we have a signal called load? Well, we had a signal called mem read enable. Okay. But let's say we did have a signal called load. Okay, then if we have the signal with a prefix of IDEX, that means that that signal is the load signal that's coming from the IDEX register, which, if you remember, the convention for naming our pipeline registers is we name them after the stages that they're between. So the IDEX pipeline register separates the instruction decode stage from the execute stage. Okay, so if you can imagine, in fact, let's go locate where that would be in our diagram here. Okay, so the IDEX is here. So let's say the load instruction came from our decode unit. I borrowed this code a long time ago, and so I don't know if I actually at the time had a signal called load. I don't believe I'm having you all specify a signal called load. It would essentially be the mem read enable, and so anyway, let's just pretend that was coming from here. Well, then when it gets latched in here, okay, into the IDEX register, then the signal coming out, that's your load signal, that would be specified as the IDEX underscore load. Okay, and that that separates it from, okay, the version that's latched into the EXMEM pipeline register. So load would conceivably, yeah, see, even in this diagram, I call it mem read enable. So I don't know, at some point I called it load, or that's just an example. I don't know. Well, so let's just say this load signal, or also called mem read, would go into the EX mem pipeline register, because it's actually, that signal is consumed in the memory stage, right? So here's our memory stage. And of course, we know this is our execute stage. Okay. So there's going to be 3 copies of this load signal in our pipeline. We're going to have the signal that originally is generated in the ID stage. Okay, we're going to have the signal that propagates through the EX stage. Now, it's not used in the EX stage in our simple pipeline. It's actually used in the MEM stage. Okay, so then we're going to have it go all the way to the MEM stage. So there's 3 different copies of this signal. Okay, well, it's not the same signal because it's separated by pipeline registers, but it's a signal with the same name. So then in the EX stage, it would have the IDEX prefix. In the MEM stage, it would have the EX MEM prefix. So hopefully that makes some sense to you here. Okay. All right. Continuing on. Okay. If only one stage is specified in the prefix, the signal originates from the given stage. Okay. So, for example, this load signal, okay, would be generated in the decode stage. It would come from the decoder, right? And so then it would be given the prefix ID. Okay, so going back to our diagram, here in the decode, this would be ID load, right here. Okay. If no prefix exists, the signal is assumed to be contained within only one pipeline stage. Okay. So you may have potentially signals that only ever reside in one pipeline stage. Okay. In fact, I see an example right here. I'm going to circle it. Here's a signal right here that comes out of the ALU decode unit and goes right into the ALU. It's not used in any other pipeline stage. Okay? No other pipeline stage. Just this one. So in that case, if you follow my convention, it doesn't need a prefix or suffix because it's used just in this one stage. Okay? So and you can probably see a number of other examples, right? Depending on how you write your code, you might have more intermediate signals, and so you can for those intermediate signals, you don't have to provide them a prefix or suffix. Okay. All right. The suffix indicates the destination of a signal and is added to a signal name only when necessary. Yeah, we don't want to cloud our signal names because if we just add prefixes and suffixes when they're not needed, then our signal names could get arbitrarily large. But sometimes we need a suffix when we want to differentiate. So we have two signals that kind of have a similar function, but one's destined for one stage and the other one's destined for another stage. Okay, and the example that I give is and you all have already dealt with this signal, is the data mem forwarding control signal. There's actually two of those signals that your forwarding unit generates because there's two muxes, okay, but in different stages. Okay, so there's a mux in the EX stage and there's a mux in the mem stage, and that's designated with the suffix _EX and _mem. Okay. There may be a couple other signals that require a suffix, but they're definitely not as many. Okay. But anyway, this is an example where they share the same name just because they basically serve a very similar function, but each one is destined for a different stage. Okay. So only in a situation like that should you use the suffix. So. If you have any questions about the naming convention, post those questions to the discussion board. Other folks probably have similar questions. Okay, I've provided the skeleton code, which is what we're looking through here for the pipeline, and there should be a few examples of how I use this. Okay. Okay, let's just go through this line by line, and we'll continue to grow our HDL skills. So, as we mentioned before, we have to have all the library declarations up here at the top. Okay. And then we have the entity here. Okay, so the entity of our pipeline, and so the inputs, we have single cycle, which are single bit width, which are standard logic type. Inputs, which is clock and reset, and then we have our program counter, okay, which is an output, and that's a standard logic vector 31 down to 0 because that's a 32-bit bus basically. The input is we have an instruction, okay, and it's a standard logic vector 31 down to 0, so it's a 32-bit input. Okay, so that's the output from our instruction memory, which is emulated in the test bench. Okay. Similarly, on the data side, we have the data mem address, which is an output from the pipeline, and it's a 32-bit bus. And then we have other outputs that control the memory. We have a data mem read enable, a data mem write enable. Okay. And those are single bit vectors, so standard logic type. And then we have as input to the pipeline, we have data mem read data, okay, and that's a 32-bit input. And we have one more output, which is data mem write data, and that's a 32-bit output. Now, notice, last time I had talked about organizing the ins and the outs, and obviously I didn't do that here, okay? I kind of have things divided up amongst functions. So if you look here, everything below this line is your data port, or your port to data memory. Um, Between the two lines is your port to instruction memory, and then the top line is your standard clock and reset. Okay. Now in a more complicated processor, you're going to have a few more inputs and outputs, but not a lot more, actually, interestingly enough. The other thing I want to point out is I don't know if I showed you an example of this last time, but you can actually put uh, single or like type um, ports together on one line. Okay. Um, and so like clock and reset are both inputs of standard logic type. So we can actually group them all together on one line. Okay, now wherever you go to work, you may have a style guide that doesn't allow that. We try to discourage that in our style guide, but sometimes it just makes sense. So we don't adhere to that requirement um, all of the time. But I just wanted to point out that that is a legal thing the language allows. And you can do the same for standard logic vectors, like all the 31 down to zeros, all the inputs you could group together, like instruction and data memory could be on the same line. And because of the way I instantiate the the pipelined component in my test bench, okay, I do it such that it's independent of the position of the port. So you can arrange these ports in whatever order you'd like. Okay, you just have to make sure that what is an output, that the ins and outs are right, and that the width is correct. Okay, otherwise it's not going to work. Okay. Again, if there's anything that I'm saying that's confusing, just post questions to the discussion board. Okay, so we have the architecture, and again, I just went ahead and named it the same thing. MIPS of MIPS. MIPS pipeline is our component name, which is this part of line 61, and then the part that I have circled is the name of the architecture, because again, VHDL allows you to have multiple architectures defined for a single component. We're only defining one architecture here. Okay. All right. So then we have all of our component declarations. So I've provided only one for you. Okay. I've provided you the register file, and it looks like I didn't even complete it. So you're going to have to go back and open up your register file and fill in these missing pieces of the component declaration. Okay, and likewise, you're going to have to put in all of the component declarations of your other components. So your ALU decoder, your instruction decoder, all of those, your forwarding unit, your pipeline control unit, all of those components need to be declared here, and the order doesn't matter. You can declare them in any order. Okay. So really, that's the easiest way to get started is just declare all your components. Okay. And then we want to declare all of our intermediate signals uh, following our components. I don't think there's anything in the language that requires that ordering, but it just makes things a little easier. And the other thing is and line 79 kind of gives you a little bit of a tip, is that you could declare your signals in really any order, but it's a lot easier if you actually declare them in the order that they're first encountered. Okay. Now what I do a lot of times is I don't really fill in the declaration. I don't really declare signals until I'm actually writing the code. So I'll jump down to the section where I actually start filling in the code, and when I need to describe a new signal, then I go up and I go into my signal declaration and I go ahead and put it there. And that's why they naturally end up being ordered in the order in which they first appear, because that's usually how I actually fill that section out. Okay, it's impossible for you to know a priori what are all the signals you're gonna have. I mean, because you'll know as you start to write the code. Okay. Okay, and so here are a number of examples, but don't think that this list is complete. I left some of them in here, and I probably left a lot more signal declarations in here than normal, because I kind of wanted you to follow this convention, this naming convention. And so I almost named a lot of the signals for you, okay? And so we can see each of these, like, let's just follow some of the signals starting in decode. So we have IDRS, IDRT, and looks like those are all the signals I defined for you in decode. But all of the signals that come out of your decoder, those all need to be declared here, right? Because you have to wire them up, okay? And then if we go into the execute stage, we have a number of signals here, like our ALU in and shamped and ALU in B. Okay, let's see, shamped. Shamped would basically be this signal here. Okay. But like ALU in A and ALU in B, those are and shamped, those are examples of signals that are only generated and used in the execute stage. So notice they don't have any prefixes or suffixes, okay? Because they're only used in the execute stage, okay? Now, the ALU result, that propagates down the pipeline. So, so notice that it has a prefix of EX, and that's because it's generated in the EX stage. Okay, so if we go locate on the diagram, the EX ALU result is this signal right here. Okay, it's generated in the ALU. Okay, and then it simply goes right to a pipeline register. Okay, so you're going to declare it's declared here. Okay, on line 94. And when you instantiate your ALU, you're going to wire up that particular output. Let's see if I have an example. Let's see. Okay, no, I didn't instantiate the ALU for you, but there's a comment there reminding you to do so. How nice of me. Okay. All right, well, if we look at the diagram, ALU result continues. It goes in as the address of the data, and then it continues off here through the mem stage, and then it even exists in the execute stage. Okay. So let's go look at our signal declarations. So, and notice I have the signals divided up into pipeline stages. Okay, that just makes things a lot easier. Organization is key here. All right, here we go. This is the ALU result in the mem stage. It's given the prefix EXMEM, which indicates that it's coming from the EXMEM register, which we see here. So that's this signal here. Okay. Now, I mentioned it's also tied into your address. So that means you're going to have an assign statement that assigns um, the data mem address to exmem ALU result. Okay. I don't know if I provide that line for you. No, I don't. Okay. So anyway, you'll have an assign statement. That's how you actually wire up the ALU result to that output port. Okay. Well, ALU result also exists in the write back stage, and there it's stored in the mem write back pipeline register, and so that's this chunk right here. Okay. So that's going to feed into a mux that you're going to describe in the write back stage. Okay. Okay, and so I have a number of signals here. I don't know that I don't think these are complete. There's probably a number that are left out here, but hopefully it's enough. Hopefully I left enough in there to give you an idea of what to do here. Okay. So then we have the begin statement. So after the component and signal declarations, then we have a begin statement, and that starts the actual logic. And at line 123, I kind of just tell you, hey, here's your instruction. I have a comment that says, hey, this is the instruction fetch logic. And then at 125, I say, yeah, go ahead and insert your PC logic here. Okay, marking the beginning of the fetch stage. Okay, so if we go into our diagram, that's this part, right? So we've got a mux and we've got the program counter. And you should have already described a program counter in your single cycle design. Okay. Now, the only difference is you're also going to have this PC write. So you're gonna gate writes based on that PC write being asserted. If the PC write is not asserted, the program counter just stores the previous value it had, so it doesn't do anything. Okay. And I've got an example of how to describe that here in a second. Okay. Okay, so then I give you, I start the IFID pipeline register for you. Okay, so here I have a comment that says, hey, this is the IFID pipeline register. Okay, this marks the end of the fetch stage. Okay, and which at the end of it here, see, notice our decode logic starts at the end of this pipeline register. This pipeline register separates the fetch and decode stages. Okay, so we're using a process block. This is a register, so it's sequential logic. It's sensitive to the clock, which is what having the clock in the sensitivity list here tells us. Okay, process parentheses sensitivity list. Okay, that's how these process blocks are supposed to look. And so sequential logic like this, edge-triggered logic, is only triggered on the clock. If it's an asynchronous reset, you can have the clock and the reset here. Okay, but I don't have you worry about, for the pipeline registers. I don't have you worry about that. Okay, in a real design, your VLSI guys may have you put resets on all of your flip-flops because it makes verification a lot easier. Okay, and most of the time the flip-flops have a reset port. So if you don't specify a reset capability, they just leave that port tied disabled basically. So it's not like adding reset makes your flip-flops larger. Okay, it just means you're not using features of the flip-flop, if that makes sense. So, okay. So line 130 says if clock event and clock equal 1. Now you can also replace that with a rising edge statement. Okay, so there's newer statements in VHDL that allow you to specify the same thing. This basically is saying, hey, when the clock changes and the clock is high. Well, that basically means it's looking for a rising edge. Okay, if you said if clock event and clock equal to 0, that would be a falling edge. Okay. And again, you can use the more modern aspects of the language, and you can replace that clock event and clock equal to 1 with a rising edge statement of clock. Okay. All right. So what that basically means is when anything in your sensitivity list changes, then you can think of it as it's going to evaluate whatever's in this process block. And this if statement at line 130 is written such that we're only going to consider the rising edge of the clock. Okay. Okay. So, what's interesting about this particular pipeline register is you remember with our discussion with the pipeline control unit is we needed the ability to flush a particular instruction, okay, that's in this register, in this pipeline register. Okay, so that's what line 131 does. Okay, so if the flush IFID signal is asserted, then set everything in that register to 0. Okay, that's what that does. So when the pipeline control unit wants to flush an instruction, okay, this is how it does it. It will assert the IFID, the flush IFID signal, okay, which is going to flush the instruction in the IFID register. Okay. Now I have a note here to add more registers here. The first register that I define here is the instruction. Okay, so let's go locate this in our diagram. See here? See how the instruction is fed in here? So I'm describing the register, that portion of this pipeline register that stores the instruction. And here is the ID flush instruction. Okay, or signal, I'm sorry. Okay. Other signals that you need to have in this register is the PC plus 4. Okay. So you'll have to add that. So you would add it here on line 133. Okay. Now what's interesting is you don't actually have to allow the address, the PC plus 4. That doesn't have to actually be flushed. So it's up to you. If you wanna set that to 0 when the flush IFID is asserted, you can. If you don't want to, you don't have to. We only need to flush control signals. That's all. And specifically, we only need to flush the control signals that write state to the processor. Now, in the case of the IFID register, that stores the result of fetch, and well, at that point we haven't decoded the instructions, so we actually have no idea what the control signals are. So we literally, line 132 literally just sets it to a no-op, because if you remember, I think we talked about that. Is a no-op is all zeros. So when the instruction is all zeros, that's a no-op. So this is literally transforming the instruction that was fetched, okay, that's in the IFID register to a no-op. Okay. Okay. So if the IFID flush IFID is not asserted and the write IFID is asserted, then we go ahead and we latch. Okay. And so we'll go ahead and store the value from the signal from the IF stage. Okay. Now this instruction, I'm not following convention, right? If I, if I was following proper convention, I probably need to correct this. This would be called the IF instruction. I guess the reason I'm not following convention is because instruction is literally one of our input ports, I believe. Yeah, here it is. Let me erase this sea of mess here. Yeah, it's one of our input ports. See, so we're just directly wiring that in. So you don't have to follow convention for that one, right? Okay. So this allows us to stall. Okay. If the write enable for the IFID register is not asserted, then we simply hold the previous value. So when we want to stall the front end of the pipeline, our pipeline control unit sets write enable for IFID to 0, and it'll just hold the previous instruction. Okay? Yeah, because notice there's no else here. You don't need an else. It's implied. Since there's nothing else that you do, if both of these two conditions fail, if your condition at 131 and 134 fail, then you don't do anything. Which not doing anything is essentially just holding the value you had before. Okay. Likewise, when write enable for the IFID is asserted, which is during normal flow of instructions, it'll go ahead and latch the value that was fetched. Okay. So that's your first pipeline register, and of course I also have add more registers here because we have to add the PC+4 register. Okay. Which I don't know if it doesn't look like I provided the signal declaration for that one, so you'll have to come up with that. I did for the IFID instruction here, and the flush IFID write enable. Okay. So then we enter the decode stage, and I notice I separate these stages with dashes. It just makes the code a lot easier to read. And here we, the first thing we do with decode is we basically take the instruction, which if we go back to our diagram here, okay, erase some of this. So here's our instruction coming from the IFID register, okay? And notice it breaks off into little chunks, okay? Well, that's described here, see? So we take the IFID instruction, okay, and we break up into ID RS and ID RT. And of course there's a lot missing here. We need to instantiate our register file. We have to instantiate our decode, and what else is in the decode stage? Let's see. Well, we're going to have our pipeline control unit. We're going to have our forwarding unit. You'll also describe the sign extension in this stage, along with you'll calculate the branch target. So you'll do all that in this stage. So there's a lot missing here. Okay. And I started the instantiation of the register file. Okay. So notice here we lines 144 and 45, we went ahead and created the ID RS and ID RT signals, and then in the instantiation here, we're wiring them up to our register file. Okay. So that's, if we go back to the diagram, that's describing this part here, right, where we wire them up to our register file, here and here. Okay. And similarly, we have the here's kind of a fun one. Remember this: the right red signal wraps back around. Okay. If we go look at the diagram, it comes from the right back stage, right? So here it is. This is the signal, and it's coming all the way over here, coming from the right back. Okay. Whoops. 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 It's not giving it the gestures I wanted it to. Okay. Well, here it is. Look at that. And again, that right red signal flows down the pipeline. Okay. If we go back to the diagram, hopefully I'm not getting you sick here. Flipping back and forth here. You know, that signal is generated in the EX stage by this mux here, and then it flows here into the mem stage and then to the right back. And so it's following our naming convention here. So if it comes from the right back, it's the mem right back right reg signal. Okay. Because this prefix indicates that it's coming from the pipeline stage that separates the memory and the write back stage. Okay. Now clock, of course, is wired to everything. That goes everywhere. That one's easy. That one has no prefix or suffix. And then write data. Okay. Write data comes from a mux that's in the write back stage. So that's why the prefix only has the write back stage, because it's generated in the write back stage. Let's go look at where it's generated. It's generated right here. There it is, in the write back stage. This is the signal we're talking about. See, so hopefully I'm convincing you that this naming convention makes it a little easier. Like I say, the hardest thing about writing good HDL is coming up with good, meaningful signal names. And so hopefully I've taken care of a lot of that for you. And in the future, you can follow these similar conventions, hopefully. Okay, and then the EX stage. Okay, so again, there's a whole bunch of things missing here as well. But here's where we generate the SHAMP signal. And, you know, so with SHAMP, the lower 5 bits, 5 down to 0, is bits 10 to 6 of the instruction. And it's, so, well, what instruction signal is it? It's the one coming from the IDEX. So, oh boy, this diagram's getting messy. So let's do some cleaning up here. And there's a long lag. There we go. This poor little mobile core processor's doing the best it can. It even gets warm. I have to, you know, I obviously don't run it on battery when I'm recording these lectures. Okay, I forgot what the hell I was even doing. Okay, let's go back over here. Oh, SHAMP. Yeah. Okay. So here in the diagram, we see that it picks off from the instruction. See, this is our instruction. Okay, it comes from here. Ultimately, it comes from the instruction memory, goes to the IFID, goes to the IDEX, and then here it is, and this becomes SHAMPed, and then we feed it into the into our ALU A mux. Okay, and now of course we have to pad the upper bits, or zero extend with 0. Okay, because we have to convert it to a 32-bit signal. Okay, and so we just fill it with zeros. Okay, and then we have it looks like I wrote the entire ALU source A mux for you. Okay, well that was really nice of me. Okay, so let's look at it. So if we looked at the diagram, the very first input is SHAMPed. So when the select line is 0, 0, we set ALU in A to shamped. Okay? And our select line is the IDEX ALU source. And if you remember, that signal, that ALU source A, is generated from your pipeline, your forwarding unit in the decode stage, and then it's registered in the IDEX pipeline. Okay, let's go back to the diagram and follow that path. Okay. So it's generated in the forwarding unit, and then it's latched into the IDEX pipeline register. And see, here it is. This is it right there. Okay. And we're using a with select, which is a really nice, elegant way of describing a multiplexer. And so with IDEX ALU source, it uses that select. So based on IDEX ALU source, it will set ALU in A to one of these 4 values. Okay. So the next input is write back reg write data. Let's go look at that. I colored the forwarding paths in green. So this is a forwarding path, and it's this one right here. Okay, so it's forwarding data from the write back stage. Okay, so if you remember that, so that's 2 stages ahead of us. Okay, so in the decode stage, your forwarding unit would have determined that there's a data dependency between the instruction in decode and the instruction 2 stages ahead of us, and it would have set this signal to pull from this path. Okay. The next path while we're here is this other green path here. Okay. And that comes from the stage immediately ahead of us. Okay, it's right there. Whoops. Didn't go in there. There we go. Okay. Alright. So we see that. Okay. When our select line is set to 1, 0, it grabs it from the EX MEM ALU result. We already talked about that signal. Okay. There it is. Okay. See, it comes all the way from here. Okay. All right. I almost feel like I'm like Bob Ross, and you're probably putting you to sleep here. I don't know if anybody even knows who Bob Ross is. He ran a painting show on PBS, and of course everybody that has seen the show says that he was just way too laid back to be that way naturally. Okay. So anyway, I watched a little bit of Bob Ross when I was a kid, but because we talked about it, I was like, oh, I should go back and watch some Bob Ross. And I tell you, man, I started on one episode and I fell asleep halfway through it, and I must have woke up on the 3rd or 4th episode. So if you really need, some sleep, go watch some Bob Ross. I forget what the name of his show is, but you can go onto YouTube and find it if you just type in painting with Bob Ross. He was known for his big afro and everything, but he would turn everything into a tree, and he was just so laid back that you just knew why he was so laid back. So anyway, hopefully I'm not putting you to sleep, but it's just about, it is my bedtime right now, and so I'm a little tired. So I apologize. I'm not as energetic right now. We're almost through this. Okay, so yeah, and we have this when others. So we have these 3 conditions, and the only other condition it can be is 1, 1. And that's not completely true because a standard logic vector can actually take on one of four values. Uh, 0 and 1 are the ones we're familiar with, but it can also take on a Z, which is high impedance, and it can take on an X, which is undefined. And there's actually there's a few more, and I can't quite remember what they are. Um, but most of the time you don't use them except in simulation and verification. But okay, so if it was any of those other ones, it would hit this case. So whatever, not a big deal. Okay, and so it looks like that's about all I provided you, other than some comments to give you some guidance on what to do next. Okay, but I think I think we've spent enough time talking about this. So if you have any questions, do um, post them to the discussion board, and I'll try to answer them as they come in. So you have a little over 2 weeks to do this. I would use your time wisely. It's going to take a little while um, to complete this design. So, but hopefully I've convinced you that everything you need is kind of depicted in this diagram and fairly straightforward to describe. Okay, go back and look at some of your other modules and some of the example code I provided you um, to to figure out how to describe some of this stuff. Really, you're describing muxes and registers and instantiating components you've already described or developed. So that's really about all you're doing here. So anyway, I hope you all are staying healthy and happy, and have a good night. I'm gonna go to bed. So.